Hello friends, welcome to my channel Physics with Rakshi. In this series of videos on the book Theory of Everything authored by Stefan Hawking, in four previous videos we show introduction to book, origin of our universe, expanding universe and black holes according to book. In the present video we will see why black holes are not totally black. We will see black holes definition, what is Hawking radiation, what are primordial black holes, how to observe it, what is the second law of black hole thermodynamics, how by unifying quantum mechanics with general theory of relativity can answer regarding black holes. Let us start. Earlier we showed definition of black hole that black hole is a kind of object whose gravitational pull is so strong that even light cannot escape. It means black holes are things which only absorbs but not emit, and that is why it is known as black hole. In black hole, in the previous video, we show that singularity is censored by event horizon or boundary or edge of black hole. In black hole, area of event horizon increases if matter or radiation fall into it. It means if you throw matter particle into black hole, its area will be increased. Another thing is area of single black hole after collision and merger of two black hole would be more than sum of original black hole. It is analogous to second law of thermodynamics. We know that according to second law of thermodynamics, entropy either increases or remains constant. Total entropy of any system is greater than sum of two subsystems, and that is why it is analogous to this example of black hole. So non-decreasing behavior of area of black hole suggests that it is related to thermodynamical entropy. And as I mentioned, entropy either increases or remains constant. We can apply same principle of thermodynamics to black hole. And I also mentioned this equation, that is total entropy of system is greater than sum of subsystem S1 and S2, and that is also seen in case of black holes. To study this kind of results, in 80s, Jacob Bekenstein came up with idea that area of black hole either increases or remains constant, which is analogous to entropy either increases or remains constant. In black hole physics, it is known as second law of black hole thermodynamics. So thereafter, what happens? So as I mentioned, area of event horizon of black hole is a measure of entropy of black hole, as it is analogous to entropy. As matter carrying entropy fell into black hole, the event horizon would go up or increases, which is known as second law of thermodynamics. If a black hole has entropy, it means in thermodynamics we know that any object which possesses entropy must have temperature. Then and then we can assign any amount of entropy to that object. Similar to that, if black hole possesses entropy, it means it must have temperature, but it violates definition of black hole. We show that black hole only absorbs but cannot emit, and that is why it is known as black hole. If black hole has temperature, it means it must emit some kind of radiation. Let us see. So if a black hole has entropy, it ought to have temperature. A body with non-zero temperature must emit radiation at a certain rate. So black hole ought to emit radiation which is against its definition, as I told. So Hawking published this work with his colleagues like Carter and Bardeen in 1971. Thereafter, in 1973, during his Moscow visit, he met some Soviet scientists who were working on general theory of relativity, and they told that if you consider uncertainty principle of quantum mechanics, it may possible that black hole emits virtual pair of particles. So in 1973, during Moscow visit of Hawking, he met Seldovich and Starobinsky, and they convinced Hawking that rotating black holes should emit and create particles according to quantum mechanics. Thereafter, Hawking was not convinced, and that is why he started some calculation on black holes. And he found that even non-rotating black hole can emit virtual pair of particles, and he named it as Hawking radiation. So later on, Hawking found that even non-rotating black holes should emit and create particles at steady rate to prevent violation of second law of thermodynamics, as if black hole has entropy, it must have temperature, and by only this way we can stop violation of second law of black holes thermodynamics. So black hole's temperature depends upon mass of black hole, which was also proposed by Hawking. Here, black hole's temperature is inversely proportional to its mass. So what Hawking proposed, the higher the mass of black hole is, the lower the temperature of black hole will be. Another thing is, according to quantum field theory, empty space cannot be completely empty as it exhibits quantum fluctuation. And another thing is, as it means all fields would have to be exactly zero if space is totally empty, which is not possible according to quantum mechanics. Quantum mechanics says that quantum fluctuation must be there according to some rules of quantum field theory. We know that according to quantum field theory, by considering mass energy equivalence, that is, mass can be converted into energy or vice versa, and by considering uncertainty principle of complex conjugates, energy and time, we can say that frantically fluctuated energy can have quanta for shorter time. It means at space or in vacuum, quantum fluctuation must be there by means of virtual pair of particles that I have mentioned here by equation, that is equal to mc square and delta E into delta T greater than or equal to h cut by 2. In virtual pair of particles, if one particle has negative energy and another particle has positive energy, then what happens if negative energy particle falls into black hole and positive energy particle will go out? It will create a picture in such a way that black hole is emitting radiation. So negative energy particle falls into black hole would make positive energy particle appear to be emitted from black hole, and that we call Hawking radiation. And which is another thing is, greater the emission rate will make black hole more hotter. If black hole emits Hawking radiation with more rate, it means it has more temperature and it will evaporate soon with explosion. So as black hole's temperature is inversely proportional to its mass, hotter black hole will disappear with final burst of emission as giant explosion. As I told, as black hole has more temperature and less mass, it will explode with burst of rays. So according to cosmic microwave background radiation, even low mass black hole with few solar mass, you have to consider that such kind of black hole has mass very few solar mass, would require 10 raised to 66 years to evaporate completely, which is very huge figure than the age of our universe. Our universe was created, or Big Bang was occurred approximately 13.7 billion years ago. So this figure is very huge. We cannot predict by this way. So primordial black hole having small mass and higher temperature, and it is emitting radiation at greater rate, would have lifetime roughly equal to age of universe by means of X-rays and gamma rays. Here what happens, black holes are emitting radiation of higher frequency, that is X-rays and gamma rays. It means if you want to observe primordial black hole, you have to observe higher frequency rays like gamma rays. Here, observing primordial black hole is difficult by background gamma rays, similar to microwave background radiation. Though it is not positive evidence always, because background gamma rays is not always sign of observation of primordial black hole. It may come to other celestial sources. So to observe gamma ray, to observe it, one would have to detect several gamma rays of quanta from same direction with reasonable time, such as weeks. It requires large gamma ray detectors in space to observe it, or gamma ray quanta from explosion. And we cannot create such giant gamma ray detector, and that is why we have to take help of Earth's atmosphere, which is receiving gamma rays from many sources. So Earth's atmosphere itself is gamma ray detector. When it hits atmosphere, it creates virtual pairs of particles, that is known as pair production of electron and positron. By chain hitting, one gets more pairs of particles and electron shower, which is also known as Cherenkov radiation, which is crucial to observe primordial black holes. So Hawking radiation depends upon both general theory of relativity as well as quantum mechanics. It means you have to consider quantum theory of gravity to understand black hole completely. To understand Hawking radiation, you have to take help of quantum field theory or quantum mechanics with general theory of relativity. That is why I am saying these things. So it also suggests that gravitational collapse is not final and irreversible process as it is thought previously. It may open frontier of time travel, at least in principle. So by considering Hawking radiation, we can have one application of quantum theory of gravity. People often ask, what is the main application of quantum theory of gravity? First and foremost, theoretical application of quantum theory of gravity is study of black hole. You can understand black hole with more depth using quantum theory of gravity, which is the result of unification of general theory of relativity and quantum mechanics. So in this lecture, I explained definition of black hole, what is the second law of black hole thermodynamics. Thereafter, we saw Bekenstein's proposal. Thereafter, I explained what Hawking believed about black hole. Thereafter, I explained that black hole also exhibits temperature, which is inversely proportional to its mass. Thereafter, we saw, according to quantum mechanics, black hole also emits Hawking radiation by considering quantum fluctuation. Thereafter, we show what are primordial black holes, how to observe primordial black holes by gamma ray detector using Earth's atmosphere, using Cherenkov radiation. And thereafter, we show quantum theory of gravity is useful to understand black hole with more depth. Hawking also considered some of our history approach of Feynman to understand black hole with more depth. That we will see in the next video. Thanks for listening. If you like my video, please share and subscribe my YouTube channel. If you have any question regarding this lecture, you can ask in the comment section.